never a doubt. Here we are. Worksheet number 4. Let me recreate the magic of this. Hey, I was here yesterday. This is fun. Held constant. This goes up by a factor of 2, and this goes up by a factor of 2. What I did to b is the same thing that happens to the rate. Therefore, that's b to the 1. By show of hands, how many of you got that part right? Excellent. Life is still good. You're feeling like, yeah, I'm just good at kinetics. All right. And then the roof caves in because you say, now, since I've figured out the exponent for b, I'm going to hold b constant and take a look at a. And you realize in the column for b, they never held b, the molarity of b, constant. Can't do it. Okay, well, hold on. But I do understand what the issue is. In science, as we've talked about, the way we earned this 1 is we said this. Well, one thing I know in science, Mr. Bracken, is that we never change more than one thing at a time. You would not be pleased if you took your car in for service and you said, you towed it in and you're like, hey, it doesn't seem to start. If the auto mechanic came back and said, we replaced your spark plugs in the battery and by golly, it started right up. So you changed, well, so what was wrong with it? I don't know, we just changed the spark plugs and put a new battery in. Started, so was it the spark plugs or was it the battery? That's a really good question. We changed both things. The good news is it starts right up. No, you change one thing, does it start? Here, we're just changing b, and so of course we can say it's first order with respect to b. Well, we're going to have to change 2 things at once. And you know that, and that's the uncomfortable part where you're like, can't do it. Yes, we can. Watch how we do it. And the secret here, and I heard people talking about this, so I know this is within our reach, especially if you can figure it out before I teach it, holy smoke-a-doodles. Hey, I know I've locked in the exponent for b. I've locked it in. I know it's first order with respect to b. So here's what I'm going to do. I'm going to compare trial 1 with trial 2. Yeah, but you're going to, and I'm going to color code it. Since this is in red, I'm going to do that. I'm going to make this the blue step here. For reactant B, I know if I double this. Yeah, but at the same time, you're also doubling. I'm aware of that. I'm going to do the red change and the blue change at the same time. But in my mind, I'm going to split it up into 2 separate steps. In other words, I can't just go, no, I can't. I have to do it this way. All right, so I'm going to make the red change, and I'll land there. And then the blue change is going to get me to my final destination. All right. Well, but how do I know? Well, I do know that this is first order. Therefore, if I double b, it will double the rate. That's going to take me from 10 to 20. Yeah, but okay. The blue change will take me from 20 to the final, 20. Wow. No change. So I doubled this, but it didn't change the 0. Okay? By show of hands, how many of you got the first one right? Congratulations. That's awesome. And in case you're like, oh my gosh, I don't, relax. Now you've been taught how to do it. Let's go to the second problem. Same idea. Hey, cool. We got that locked in. That goes up by a factor of 2. And you know what? That goes up by a factor of 2. Hence, since I changed A, Doubling A doubles the rate, typical of something to the 1, first order. All righty. Well, now that I've got one of those exponents figured out, let's see what we can do. Well, the trials, I could compare any of the trials that I want, but I'm more of a multiply kind of guy, and I like the idea of comparing trials 2 and 3. You might call it the double-double idea. That is going to be times 2. Hey, it's first order with respect to A. And yeah, I'm going to have to change that as well. That's also a times 2 for the molarity. Well, when I double the molarity of A, since it is first order with respect to A, I'm going to break it up into 2 steps. Doubling A will double that rate from 20 to 40. I don't know what the exponent is for B, but I know I doubled it here. And there are a couple of options. And I'm going to teach through this to make sure you understand how logical this is. Hey, you know what? If this were, don't write it down, but if this were 0, if it were 0, you know, when I double that, nothing happens. This would go to 40. Oh, well, it didn't do that. It goes to 160. Well, you know what? If this were first order, when I double that, it's going to take it from 40 to 80. Didn't do that. Well, and again, by process of elimination or just hit the home run, hey, I'm going from 40 to 160. We can probably do that math in our head, but let's say I use ugly numbers. Okay, so when you doubled that, Bracken, this went from 40 to 160. It went up by a factor of 4, or 2 squared. Therefore, A is first order with respect to A, second order with respect to B. By show of hands, how many of you happen to get that one right? Excellent, okay? And again, if you're like, oh man, I'm 0 for 2. No, a teacher might want to explain how to do it. I wondered if anybody could catch the pattern, the method, okay, before I taught it. Once again, hey, thank you. Tripled up by 9. Therefore, it is A. A is changing. I tripled A, it went up by 9. That's going to be a 2 there. Now that that's locked in, let's take a look at B. Well, if I hate life, don't answer that question, but if you would hate life, you would compare trials 2 and 3. Why are you picking on 2 and 3? Well, 0.6 to 0.4? I'm just not comfortable with that at all. Well, yeah, you could go the other. Ew! I don't have to do that to myself. Instead, I'm going to compare these two. Trial 1 with trial 3. For A, times 2. For B, times 2. Well, I know what happens to A, and then change B is going to have to get me the rest of the way there. If I double A, and it's A second order with respect to A, if I double that, this is going to go up by a factor of 4. All right. And then change for B is going to go from 40 to 40. 0. Okay. How many folks got the third one right? Excellent. We have to be able to do these types of problems. And I'll be very honest with you, over the years, because yes, there will be one on the test where, hey, what if you never hold something constant? Now, fear not, we will always have one of them held constant. It's figuring out the other one, all right? My own experience with this over the years has been some students pick it up very quickly, and other folks have to be honest with yourself and say, I know he's going to put one on the test. I need some more examples, Bracken. Okay? You're going to get a few more examples, but we really want to make sure that we're able to see what we need to see in terms of how we do it. Okay? There's not a single person in here who should say, I don't know how to do that, so well, I just lost 4 points. No. Okay? So come in, get extra help. I'll work with you, and we're going to make sure everybody's good on that. Okay? I want to hold off on the back side of this worksheet until we've done another page of notes, which are coming at you right now. Here we go. Notes number 2. Notes number 2. So I think this is pretty easy stuff. All right. If we look at this, Kinetics Notes number 2. We're just going to get to the front page today, the first page rather. Reaction mechanism is all about how or why, I'll put how here, underneath the arrow. How does that happen? And you know, if we think about it, elementary students and elementary teachers, we thank elementary teachers for their work. It's amazing work that they do, because the elementary teacher has to know everything. They don't have the luxury of saying, hey, I'm Jeff Bracken, I teach chemistry. No, they have to know math, they have to know how to teach reading, they have to know everything in addition to dealing with recess and hair pulling and who put gum in my hair and all these joys or challenges of elementary. And so, yes, they probably should get 2 to 3 times my salary for what they have to do with their job. Now, early on in our childhood, I believe all children are naturally curious. And you might say, what do you mean? They ask great questions, and I know as a father, I was asked a lot of questions by Andrew and Adam here over the years. Hey, how did that happen? Well, there's a lot of times where we have to say, as teachers, we don't know. And that can be difficult, okay? For instance, if you're like, yeah, but Mr. Bracken, you know, we could ask you, hey, Mr. Bracken, phenolphthalein, acid-base indicator, persistent pink, yeah, drip, drip, drip. Oh, we're done, look, beautiful pink. Hey, Mr. Bracken, why does that show up as pink? Yes, it is pink. Yeah, but, well, you know, that's the perfect acid-base. It's a 1-to-1 ratio. Yeah, but why not like green? Because it's phenolphthalein and it's pink. Yeah, but what is it at the molecular level that makes it pink? It's pink, okay? A lot of times we don't know. Now, those of you who happen to know Dave Weiner, Dave has an unlimited bank of knowledge. In fact, way back in the day, they used to say, hey, let's get Dave talking about how cannonballs are made. And we won't have to learn physics. He'll just talk, and they would come back around the corner, because they used to teach in Miss Isaac's room. They would come back around, the former students of mine who were taking honors physics, and they'd be like, 38 minutes of how cannonballs are made. We didn't cover any physics today. Wow. And that was not even, hey, Dave, tomorrow we want to ask you about cannonballs. Could you kind of hone up on cannonball science? He just knew that. So Dave knows an awful lot of the how and the why, and sometimes it does take 38 minutes for a full explanation. Mr. Campbell does somewhat similar in the world of life science. Many times you've forgotten the original question, but that's okay. Campbell's got a lot of knowledge there too. So here's what I show, and this, Nicholas, I know you're going to blow me out of the water with this, but the Rubik's Cube idea. Okay, now I bought these at the dollar store over by Roush Hardware, so I don't move them very much. That's still shrink wrapped. But I remember walking through there and I thought, holy smokedoodles, this is a reaction mechanism. What do you mean? We start with chemical A, and you have to do a series of steps, transformations. Now you might say, turn it once. Hey, you solved it. Well, yeah, I suppose. But for most Rubik's Cubes, it is a series of steps. It doesn't happen all in one step. Most chemical reactions, it's not just two bumper cars, doink, done. It's the Rube Goldberg machine. Maybe you had to do that project in middle school. Or the mousetrap game, or you're big into stacking up dominoes and you're like, boop, okay, gonna go up the ramp, hit the ball goes down here, then it lands there. That is what a reaction mechanism is. It's a series of collisions. The bing bumped into bang, which then did that, which then fell apart, and holy smokedoodles, there is my final persistent pink color. Oh, I thought it was just bing bang. No, it's a series of steps. And if you are the naturally curious type, and I'll end with this idea here in terms of the mechanism idea, if you're like, well, I've kind of stopped asking how that happens. Yes, I know Jeff Bracken, the student, would have said, hey, I'm kind of wondering, why is phenolphthalein pink? And the teacher might even offer a beautiful explanation. And at the end, I would be like, hey, Mr. Wiener, I have a question. Do I have to know that on a test? No. Okay. Thank you for telling me, but I don't care anymore. Okay? So if you're like, hey, but when do we have, if you become a teacher, I can tell you that's when my curiosity went through the roof. You're walking through Kroger, Meijer, whatever, pushing the cart, and all of a sudden you go, what's up with 4 different kinds of salt? I must learn. What? How do you get all NaCl? Okay? The curiosity will eventually come back, but we in education tend to beat it out of you. Or if you're like me, for Friday's test, do I need to know that? No. Okay. Forgive me for asking. Okay. All right. Here we go. So I think the notes are pretty easy here today. Elementary steps, they did a good job naming that. It's a series of collisions. Okay? Don't worry about that part. Multi-step mechanisms. That's what you're going to see. Multi-step mechanisms. You don't solve the Rubik's Cube with one rotation. No. It doesn't work. Okay? Now, I don't like how I've written the notes, and so I'm going to highlight to make sure you find everything that we need. In fact, I would box this up, highlight whatever. I want you to see that that is an overall chemical reaction. Okay? Now, logic would tell us this, and it's wrong, and that's why I like this example. Oh, NO2 reacts with CO. Yeah, I bet they just bump into each other. Yeah, I'm just going to give the oxygen to the CO, because I know what I start with and I know what I end with. So, of course, I can piece it together in my mind. Well, when they studied this reaction, holy smokedoodles, look what happens. 2 of the NO molecules, and I'll just draw it like this. What happens is this oxygen here goes over there to make an NO3 and leaving behind an NO. NO3? I didn't add any NO3. You're right. It was formed in the reaction. And I want you to write this. Draw that arrow. Because we made NO3, but look, it gets used up right away. NO3 was not there at the beginning, and NO3 was not there at the end. It's kind of like, hey, let's drive to California. Well, if we head straight west, at some point, more than likely, we're going to drive through Iowa. And you might say, wow, your vacation was to Iowa. No, it was to California. But you went through Iowa. Yeah, we drove through it. How'd you like Iowa? We didn't get out of the car. We drove through it. So you went to Iowa. We were there for a while, but we moved on. So you made NO3. As soon as I made NO3, it chemically reacted and it went away. That is the definition of an intermediate, okay? An intermediate. It was formed in reaction 1 and it immediately consumed in the second step. I also want us to add, right here where we see intermediate down below, I want you to add catalysts. Now I know we talked about it in the earlier notes, but I want it right here by intermediate because catalysts, as you know, speed up reactions without being, quote, used up. Okay? I also want you to add the catalysts are regenerated at the end to be used over and over. That's an important thing. Again, we've talked about start with 5 grams, you have 5 grams after the reaction. But you're going to see it in a different light today. All right? So as you write that down, I want to show you this. Science, yes. And for some of us, the series of 3 funnels, and those of you watching at home, I've got 3 glass funnels stacked vertically. This may hit a little close to home for some of you. I'm going to pour water through, or say the reaction is going from the top to the bottom. 3 different steps. I'm reminded of my own high school experience. Hey, let's all go see a movie. I'll pick you up at 6:30. There's always that one friend of yours who's never ready. Maybe you're that person. You pull in, you pick up, and if it's like this, you pick up your first friend. Hey, I'll be at your place 6:20, your place 6:30, your place 6:35. 6:20 arrives, there you go, we're on our way. He or she is not ready yet. It's predictable to some extent. Is it always the second friend? Not necessarily. Again, sometimes strategically, even though people may live closer, or you just tell them the wrong time. Okay? Once I get this slowpoke, we'll be on our way to Easton for the movie. Okay? The slow step controls everything. The slow step controls the overall rate. In other words, there's not a single person in this room who right now is thinking, you have to go faster, Bracken. Replace this funnel. No, that's not going to help anything. It's the same thing if you might think about the teacher who has you do something where you're like, okay, I want you to cut this with the scissors, then tape this here, and then, I've got this one stapler here. And if I have 25 sets of scissors and 25 sets of tape and one stapler, the teacher isn't very smart if he or she says, let me go get some more scissors. No, we're all waiting on the stapler. Oh, more tape. No. The rate determining step is the slow step. Now, in case you're like, well, but what about the slow step? It's not that person's fault, or but these 3 funnels could represent Olympic sprinters, world-class sprinters. If you have 3 sprinters, one of the 3, despite being some of the fastest people in the world, one of them would come in 3rd place. Nobody ties. Somebody's going to be the slow person in that race. There is always a slow step in a series of reactions. And that is what we call, if you flip the page, they did a great job of naming it. It is the rate determining step. That slow step dictates the overall rate. Much like your friend, we're not going to get to Easton on time. Okay, I got to find a way to get this. Everything's going to be on this person. Okay. Let's take a look at this. Again, I can summarize this nicely, I think. Here is the overall reaction. Elementary step 1, elementary step 2. I remember wondering how will I know what is the slow step? Will there be like numbers? No. It's going to say slow. One step will say slow, and the others will say fast. So watch how easy this is. I know don't read all that other stuff. It's crazy. Rate is equal to K times the reactance of the slow step. Rate is equal to K times NO2 times NO2. Well, wait a minute. NO2 times NO2, that's NO2 squared, right? Final answer, out the door. Rate is equal to K times NO2 squared. Done. It's that simple. It really is that simple. Okay? Let's take a look at an example here. Hey, there's step 1, step 2. Okay, the balanced equation. We've done this back in the world of equilibrium. We're going to add two equations together, just like in math. We're going to add the yellows, we're going to add the blues. And if I do this, I'm going to write it out here before I go down to that line, because there's some canceling and combining that I can do. But I'm not even thinking. I'm not thinking. I'm just writing. Arrow HI plus HCl plus I2 plus HCl. As we've seen before, if they're on opposite sides, they cancel out. Hi, goodbye. If they're on the same side, we add together. We combine. If they're on the same side, we combine. And so, look at this. Here we go. H2 plus 2 ICl, arrow 2 HCl plus I2. Now, what is the intermediate in this two-step process? HI, you bet. I am formed in the first step and I am consumed in the second step. And what is the rate law? Oh my gosh, could it be this easy? Rate is equal to K times the reactance of the slow step, H2, times ICl. Boom. Now at this point, I want you to go to worksheet number 4 that we just did the front side. I want you to flip that over and take a look at the back of that. All right? Okay. While you're doing problems 4, 5, and 6 or whatever on that page, I'm going to go through part of number 4, but I want you to see if you can get it right. So I'm not going to say anything. We're on the back of worksheet number 4. We're on the back of worksheet 4. The overall reaction, I'm going to write fairly small. I got rid of the I because it's on both sides. Okay. For the rate law, reminder, I go to the slow step, and it would be the reactants of the slow step that are used in the rate law. All right? How many folks got A and B right? Okay. All right. The intermediate. Kyle, what'd you get for the intermediate there? The reactive intermediate.
O2? O2?
O2? No, not that. The reactive intermediate. Kayla? IO with the -1 charge. And what we mean is it was produced in the first step and it was consumed in the second step. So that would be the intermediate. Okay? We made it. I didn't add it to the beaker, and it wasn't there at the end. It formed along the way, but it was used up. The catalyst, Ruben, catalyst would be what? All right. Now watch how I draw this, because I think this is going to help a lot of folks. Let me erase the clutter, because I'll tell you, up until I saw this problem in the textbook, I just memorized the definition of a catalyst. Hey, what you start with, you end with. 5 grams, doesn't get used up. But I never understood how that worked. To me, and the answer is the iodide ion, I-, we added it at the beginning. It goes away, it's transformed into something else, and it is regenerated at the end, much like a tour guide. Okay, everybody, come with me. Hey, where's Mr. Bracken? Oh, he left with the group. Oh, no. Don't worry, he'll be back. And you come back after the tour, and you're like, hey, you guys were a great group. Hope you enjoyed your time. Next group, come with me. That's basically what the catalyst is doing. Hey, reactants, we're going to react, get our hands dirty, we're going to wash our hands, and we're going to start over and over and over. And that's why you never say to a builder that you go through a lot of hammers. No, you just don't, okay? It's a tour guide, and it goes over and over and over. Please take a moment and go through the rest of this page. I'll drop an answer